Hello friend, today we will learn about high performance architecture. So in this lecture we will discuss about how to increase or enhance the performance of any computer system. In other words, we can say that we will just enhance the throughput, or we will increase the IPC, that is the instruction per cycle. So the question is how to do it and why do it. So in our computer, in today's computer, we used to deal with lots of data, and that need a very high speed computing system. For that we need to enhance our computer. Instead of having a scalar pipeline system, we need to have more than that. So how to do it? So let's begin our journey. After the completion of the lecture, in this lecture we will be discussing up to ILP architecture, and in our next video we will see the other parts of these topics. So the first part is the classification. So let's move forward. So the under the classification we can see here there are so many parts in which we can classify our architecture. One of the most important one is the Flynn's classification, and the rest of that are also very important. These are Flynn's, handlers, and modern. So we will look forward to Flynn's classification, what it is, and the concept behind this. So let's move on. Flynn's classified the instruction and databases. He classified into 4 categories on the basis of the instruction, the number of instruction that would be faced by the memory, by the control unit, and after that it will be processed in the processor, and how many data stream it will be able to process. According to that, he classified into 4 categories, as you can see here: single instruction, single data; single instruction, multiple data; multiple instruction, single data; and multiple instruction over multiple data. So one by one we will see the concept behind each, and we will try to understand the core concept. So let's begin. The first one, that is SISD. In SISD, as we can see here, the control unit is it is here present over here. The control unit is taking a single instruction from the memory part, and after fetching the control unit, fetching the instruction, the instruction is then transferred to the processor. Here the processor processes it and produces a data stream, that is DS, and it will just write back to the memory. So as we can see here, there is only one instruction that is moving from from the memory to the control unit, and from the control unit to the processor, and only one data stream that is passed to the memory. So that's why it is called SISD, that is single instruction, single data. Now what is SIMD? As the name itself says, SIMD, that is single instruction, multiple data. So we will take a single instruction from the memory and fetch to the it will be fed to the control unit, and this instruction is then be executed by several processors. As you can see, the dotted line here present over here, this signifies that there are there is not a single processor. There are so many processors present over here, so the single instruction is processed according to the processor present over here, so it will generate a multiple number of data streams, and these data streams will now feed back to the memory part. So what happened? So here we are taking a single instruction, and in this single instruction we were executing via several processors. So to produce a multiple data stream over a single instruction, that is called the SIMD processor. Now MISD, so again here the name itself says multiple instruction but over a single data stream. So we will take not a single instruction, but we will take multiple amount of instruction. As you can see here, there is a multiple instruction and it will be processed according to the processor, and each processor will generate a single data stream, and this will move to the memory unit. So we can say that MISD, in which there is a concept of multiple instruction or over a single data. Now move forward. MIMD. Here MIMD, we will take not a single instruction and also not even a single data. We will take multiple instruction, and it will be executed by various processors that produces multiple data streams, as you can see here. So as I think you may be able to understand the concept behind the Flynn's classification, and now let's move forward to our next topic, that is ILP architecture. So what is ILP and why do we need this? ILP stands for instruction level parallelism. So in our scalar pipeline, there was a bounded performance. We can say there is a foundation for the performance, as we were not able to increase the throughput up to a desired limit. So to increase the IPC or to decrease the CPI, we need to have a ILP architecture. So the demerit, as we can say, the demerit for scalar pipeline was maximum throughput bounded by the one IPC. So we were not having more than one IPC. That is a one point, as we can say, where after achieving ILP we can increase IPC, and we can also decrease the CPI. In other words, the second demerit for the scalar pipeline is there is a rigid nature of in-order pipelining, and in these demerits are overcome by the ILP architecture. So let's see. So in ILP we will study pipelining, VLIW and superscalars. As you must have an idea for the pipelining, what is pipelining, and the concept behind, the basic concept I would say, because there is not very much more things to learn for the pipelining. As we know, a single task is break down into several tasks, subtasks we will say. and each subtask is performed or executed by by multiple functional units at the concurrent time. So as the instruction is subdivided into IF, that is instruction fetch, decode, and we will just execute and write back to the memory. So there is a simple multi-cycle design, as we can see from here. Resource sharing across cycles. All instructions may not take same cycle. Why? The question is why. The question is why, and the answer is, as we have seen, there is always a hazard associated with the pipelining. So if there is any hazard comes in between the processing, then the software will be stalled. So after stalling the process, the whole processing unit will pause for a few minutes or few seconds. That will not be a minute. It will always be in nanosecond or microseconds. So we will have to wait. So that's why, that is the reason all instructions may not have the same cycles. And another one is a faster throughput with the pipelining, as the linear execution will not be able to give us the throughput as the pipelining gave to us. So these are the hazards. Mainly there are three types of hazard. These are the control, data, and the structural hazards. We will see these hazards in a very vivid way, I would say, in a very vivid way in our next video. So let's move forward to our current topic, pipelining performance. So as here you can see that there is as number of stages divided. Here it is a single instruction, and it is divided, subdivided, I would say. It is subdivided into multiple parts, and each part is executed by different functional units. So the main thing is, for the ILP is VLIW. The VLIW, first I will explain the concept behind it, and then I will prove why the name VLIW is. So in VLIW, it is mainly a compiler based, as the compiler chooses the instructions, and the compiler chooses the instruction from the whole lot of instructions list, and then it just bundles the instructions into a single instruction. As we can imagine, an instruction is not a single one. Here we will take a bundle of instructions that can comprise 4 to 5, 6, 7, 8, up to 8. We would say up to 8 instructions it can take, and these instructions are then phased in order, and they will be executed as the pipelining process. So after this, I think you were able to understand why the name VLIW, that is very large instruction word. So very large instruction word itself says that the instruction is not a single one. It will comprises of 4 to 8 instructions in a packet. It is totally compiler based, as I've said earlier. In this, the compiler has a complete responsibility for selecting a set of instructions to be executed concurrently. So in this, we can say that there is not much of hardware component, and there must be a smart compiler so that it would execute the instructions in a good manner or in a faster manner to increase the throughput. It generally increases throughput for the instructions, because it is very much fast. As in pipelining we were executing a single instructions, but in a pipelining way, but we are here executing several instructions in a single instructions, and the processing is as like it was in pipelining, so it just increases the uh, instruction throughput. So superscalar processor. Now we will see what is superscalar. So let's begin. In superscalar, large data transfer capability between the functional unit and the registers, as it uses so many registers, so it is not a compiler based, totally not based on the compiler, it is hardware based, and so that's why the reason is um, uh, that is the reason why the hardware is very much complex in this, and there is a more component for the hardware, as it is not as like it was in what we have learned earlier, that was the VLIW. So it is not like VLIW where there is compiler based technology, but here it is hardware based technology. So in superscalar, the processing is very much fast, because we take so many instructions in one, and they were executed as it was in pipelining. So we will learn the rest of the part in our next video. I hope it helped you. Thanks.